Hey guys, welcome to the channel. This is रोहन और आज हम देखने वाले वेरिटेशन की वीडियो इनफाइनाइट पैटर्न विच नेवर रिपीट्स। कारण इस टॉपिक के बारे में ये बातें हैं, पर लेट्स सी, विल जस्ट वॉच द वीडियो, लेट्स फाइंड आउट एंड सी। एज ऑलवेज वेरिटेशन इज अमेजिंग। विल जस्ट प्ले द वीडियो। हियर वी गो। ओके।
A portion of this video was sponsored by LastPass. This video is about a pattern people thought was impossible and a material that wasn't supposed to exist. The story begins over 400 years ago in Prague. I'm now in Prague in the Czech Republic, which is perhaps my favorite European city that I've visited so far. I'm going to visit the Kepler Museum because he's one of the most famous scientists who lived and worked around Prague. I want to tell you 5 things about Johannes Kepler that are essential to our story. Number 1, Kepler is most famous for figuring out that the shapes of planetary orbits are ellipses. But before he came to this realization, he invented a model of the solar system in which the planets were on nested spheres, separated by the Platonic solids. What are the Platonic solids? Well, they are objects where all of the faces are identical and all of the vertices are identical, which means you can rotate them through some angle and they look the same as they did before. So the cube is an obvious example. Then you also have the tetrahedron, the octahedron, the dodecahedron, which has 12 pentagonal sides, and the icosahedron, which has 20 sides. And that's it. There are just 5 Platonic solids, which was convenient for Kepler because in his day they only knew about 6 planets. So this allowed him to put a unique Platonic solid between each of the planetary spheres. Essentially, he used them as spacers. He carefully selected the order of the Platonic solids so that the distances between planets would match astronomical observations as closely as possible. He had this deep, abiding belief that there was some geometric regularity in the universe. And of course there is, just not this. 2. Kepler's attraction to geometry extended to more practical questions like, how do you stack cannonballs so they take up the least space on a ship's deck? By 1611, Kepler had an answer. Hexagonal close packing and the face-centered cubic arrangement are both equivalently and optimally efficient, with cannonballs occupying about 74% of the volume they take up. Now, this might seem like the obvious way to stack spheres. I mean, it is the way that oranges are stacked in the supermarket, but Kepler hadn't proved it. He just stated it as fact, which is why this became known as Kepler's conjecture. Now, it turns out he was right, but it took around 400 years to prove it. The formal proof was only published in the journal Forum of Mathematics in 2017. 3. Kepler published his conjecture in a pamphlet called De Neva Sexangula on the 6-cornered snowflake, in which he wondered, there must be a definite cause why, whenever snow begins to fall, its initial formations invariably display the shape of a 6-cornered starlet. For if it happens by chance, why do they not fall just as well with 5 corners or with 7? Why always with 6? In Kepler's day, there was no real theory of atoms or molecules or how they self-arrange into crystals, but Kepler seemed to be on the verge of understanding this. I mean, he speculates about the smallest natural unit of a liquid like water.
तो बेसिकली बहुत ही काफ़ी इंटरेस्टिंग है केपलर के ऑब्जर्वेशंस जैसे। लेकिन एक चीज़ है कि इफ़ यू डोंट नो ऑल द थिंग्स अबाउट द यूनिवर्स, यू कैन, जो आपको पता है उससे आप कुछ एजम्पशंस बना सकते हो। एंड इफ़ यू आर अ जीनियस लाइक केपलर, सो आप जो कहेंगे वो एक कॉन्जेक्चर बन जाता है, मतलब उसका कोई प्रूफ नहीं है, कुछ एक लॉजिकल एक्सप्लेनेशन है, बट बिकॉज आप जीनियस है इसलिए आपने कहा है तो उसे हम रखेंगे। बट अनलेस इट इज़ प्रूव्ड, वो प्रूफ नहीं बनता, वो लॉ नहीं बनता या प्रिंसिपल नहीं बनता। सो काफ़ी इंटरेस्टिंग है कि कैसे स्टैक करें या प्लैनेट्स ऐसे ज्योमेट्रिक शेप्स में होंगे। क्वाइट एन इंटरेस्टिंग वे टू थिंक अबाउट द थिंग्स अराउंड यू। मे बी यू माइट बी रॉन्ग, दैट्स ओके, यू आर अलाउड टू बी रॉन्ग इन साइंस, बट यू आर थिंकिंग एंड दैट्स द फर्स्ट वे।
Essentially a water molecule, and how these tiny units could stack together mechanically to form the hexagonal crystal. not unlike the hexagonal close-packed cannonballs. 4. Kepler knew that regular hexagons can cover a flat surface perfectly, with no gaps. In mathematical jargon, we say the hexagon tiles the plane periodically. You know that a tiling is periodic if you can duplicate a portion of it and continue the pattern only through translation, with no rotations or reflections. Periodic tilings can also have rotational symmetry. A rhombus pattern has twofold symmetry because if you rotate it 180 degrees, 1/2 turn, the pattern looks the same as it did before. Equilateral triangles have threefold symmetry. Squares have fourfold symmetry, and hexagons have sixfold symmetry. But those are the only symmetries you can have: 2, 3, 4, and 6. There is no fivefold symmetry. Regular pentagons do not tile the plane. But that didn't stop Kepler from trying. See this pattern right here? He published it in his book Harmonices Mundi, or Harmony of the World. It has a certain fivefold symmetry, but not exactly. And it's not entirely clear how you would continue this pattern to tile the whole plane. There are an infinite number of shapes that can tile the plane periodically. The regular hexagon can only tile the plane periodically. There are also an infinite number of shapes that can tile the plane periodically or non-periodically.
तो अभी हम लोग जो बात कर रहे हैं कि नॉर्मल आप आपके घर में लादी में टाइल्स होंगे, आपको बिठाना है, तो बेसिकली आप क्या करेंगे, स्क्वायर लगा दीजिए, तो वो पूरा फ्लोर कवरिंग हो जाएगा। लेकिन अगर हम कोई दूसरा शेप लेते हैं, तो क्या वो बिना किसी को कटिंग के या कुछ एडिशन के क्या हम उसको पूरा लादी का कवर कर सकते हैं? तो एग्जांपल है, जैसे कि हम ट्रायंगल लेंगे, इक्विलैटरल ट्रायंगल, तो जैसे आइसोसेलेस ट्रायंगल है, सॉरी इक्विलैटरल ट्रायंगल लेंगे, तो हम स्क्वायर का 2 टुकड़ा समझ लीजिए उसे। जब स्क्वायर होता है टाइल्स तो ट्रायंगल भी हो जाएगा। उसी तरह हेक्सागन होता है, क्योंकि उसमें आप मान लीजिए कि जो शेप है वो 3 है, तो उसी तरह लेकिन फाई का नहीं होता। फाई में थोड़ा-सा वो बैठता ही नहीं मामला। आप जोड़ने जाएँगे तो बैठता ही नहीं। लेकिन केपलर ने फिर भी ट्राई किया मिक्स मैच करने के लिए डायग्राम के साथ। देखते हैं अभी कौन-सा पैटर्न वहाँ पे निकलता है।
For example, isosceles triangles can tile the plane periodically, but if you rotate a pair of triangles, well, then the pattern is no longer perfectly periodic. A sphinx tile can join with another, rotated at 180 degrees, and tile the plane periodically. But a different arrangement of these same tiles is non-periodic. This raises the question, are there some tiles that can only tile the plane non-periodically? Well, in 1961, Hao Wang was studying multicolored square tiles. The rules were touching edges must be the same color, and you can't rotate or reflect tiles, only slide them around. Now, the question was, if you're given a set of these tiles, can you tell if they will tile the plane? Wang's conjecture was that if they can tile the plane, well, they can do so periodically. But it turned out Wang's conjecture was false. His student, Robert Berger, found a set of 20,426 tiles that could tile the plane, but only non-periodically. Think about that for a second. Here we have a finite set of tiles. Okay, it's a large number, but it's finite, and it can tile all the way out to infinity without ever repeating the same pattern. There's no way even to force them to tile periodically. And a set of tiles like this that can only tile the plane non-periodically is called an aperiodic tiling. And mathematicians wanted to know, were there aperiodic tilings that required fewer tiles? Well, Robert Berger himself found a set with only 104. Donald Knuth got the number down to 92. And then in 1969, you had Raphael Robinson, who came up with 6 tiles, just 6, that could tile the entire plane without ever repeating. Then along came Roger Penrose, who would ultimately get the number down to 2. Penrose started with a pentagon. He added other pentagons around it and, of course, noticed the gaps. But this new shape could fit within a larger pentagon, which gave Penrose an idea. What if he took the original pentagons and broke them into smaller pentagons? Well, now some of the gaps start connecting up into rhombus shapes. Other gaps have 3 spikes. But Penrose didn't stop there. He subdivided the pentagons again. Now, some of the gaps are large enough that you can use pentagons to fill in part of them. And the remaining holes you're left with are just rhombuses, stars, and a fraction of a star that Penrose calls a Justice Cap. You can keep subdividing indefinitely, and you will only ever find these shapes. So with just these pieces, you can tile the plane aperiodically with an almost 5-fold symmetry. The fifth thing about Johannes Kepler is that if you take his pentagon pattern and you overlay it on top of Penrose's, the two match up perfectly. Once Penrose had his pattern, he found ways to simplify the tiles. He distilled the geometry down to just 2 tiles, a thick rhombus and a thin rhombus. The rules for how they can come together can be enforced by bumps and notches or by matching colors. And the rules ensure that these 2 single tiles can only tile the plane non-periodically. Just 2 tiles go all the way out to infinity without ever repeating. Now, one way to see this is to print up 2 copies of the same Penrose pattern and one on a transparency and overlay them on top of each other. Now, the resulting interference you get is called a moire pattern. Where it is dark, the patterns are not aligned. But you can see there are also some light spots, and that's where the patterns do match up. And as I rotate around, you can see the light spots move in and get smaller, and then at a certain point, they move out and get bigger. And what I want to do is try to enlarge one of these bright spots and see how big of a matching section I can find. Oh, yes. Yes. It's like all of a sudden everything is illuminated. I love it. So these patterns are perfectly matching up here, 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 and here, but not along these radial lines. And that is why they look dark. So what this shows us is that you can't ever match any section perfectly to one beneath it. There will always be some difference. So my favorite Penrose pattern is actually made out of these 2 shapes, which are called kites and darts. And they have these very particular angles. And the way they of kites and darts, and every picture that we see is just a portion.
You get the idea. The patterns जो है Kepler was right in a way, but he could not pinpoint क्या exactly कौन सा shape होगा. और yes, so that's the magic beauty of mathematics. That's the beauty of science. Okay, you can find something and infinite pattern, things which does not repeat, uh, with just 2 sides, 2 shapes. तो ये बहुत ही यूनिक है, बहुत ही ब्रिलियंस है. So I get the idea, and I think you also get the idea. So as always, Veritasium has brought to us something mind-bending and very, very interesting. So pattern matching is definitely one thing. Like anything, मैथ्स में आप कोई भी चीज़ आप ले लीजिए. If someone tells a conjecture, okay, and if conjecture is false or true, तो वो हमें प्रूव करना पड़ता है. We have to prove it, and the conjecture might seem silly or simple, but once you know it and once you solve it, it's like the application can be anywhere and everywhere. So it might seem like a simple thing, but its implications might be very much. So I guess you can watch the rest of the video if you want to know more about it. And I really enjoyed it. It's amazing, and loved it. It's mind bending. So hopefully we'll watch more of such videos in the future, and bring out amazing videos to you. And I'll also be doing new videos, uh, trying to experiment and finding new things for you. Okay, that's it, guys. Till next time, take care. Bye.